All right, thank you very much. So I'm going to be talking today about what you need to do to secure your devices against nation-state actors. So the first question you might have is, who really cares about hacking my devices, right? Who's going to bother to take the time? Well, if you look at the automotive industry, in the beginning, academics were like, hey, this looks like a fun thing for us to try to poke at. And, we did some of this work and wrote some papers, not myself personally, but actually a professor at NYU and a bunch of professors at Washington, UCSD. And then after this, we had the kind of the tracksuit crowd, like the DEF CON or black hat hackers who like to kind of show off and do flashy things and get more popular press coverage and be a little more reckless. And today, it's really nation-state actors that are really interested and really effectively able to do this. So these things, what often happens is academics will often show it's possible. Then we'll have kind of the black hat DEF CON crowd, and then you get nation-state actors, which is what you really need to be worrying about because you all are building things that are supposed to last for long periods of time. So now let's go back. Who cares about hacking my devices? Well, let's look at a couple different domains here. So first of all, who cares about hacking medical devices? Okay? So there have been lots of major nation-state attacks and ransomware targets that deal with hospitals and medical devices. We saw the NotPetya attack, which was allegedly Russia going after Ukraine infrastructure and that spilling over and causing massive damage across hospitals, primarily in Britain, but around the world. There tend to be somewhat fewer academic hackers than we've seen with things like cars. But I think the reason why is that these are expensive devices and most people don't just have them at hand. I was invited to go to a summit where medical device companies had brought their devices and let us try to break around and see if we could break into them with the requirement that we not disclose anything about who the companies were or what devices or any of that. But I can say that I am not like a hacker guy. I'm not one I build defensive systems. That's what I do. And I was able to break into a system like no problem in 10 minutes, had a root shell and had it displaying messages on the display of the device, like telling them the Bitcoin wallet to transfer things to in about an hour. Okay. So, and this was a device you did not want to have this happen on. Okay. As you can imagine for most medical devices. So these are actually quite scary. And hospitals have a whole bunch of things that makes it very difficult to secure them. They're very open. Lots of people get to come in and connect to their networks. And it's really difficult to know who to work with because there's 70,000 or so device makers and 70,000 or so hospitals buying things. So it's hard to secure things in this domain. Now, we're looking at consumer IoT. I think everybody's seen the news about this and seen over and over and over again how, in fact, when you look at some of the large botnet attacks, these have been from a bunch of unsecured home cameras. You can also go on certain sites and you can actually view people's cameras. There are hackers who have collected feeds of random people's cameras they've left in their home and curated those feeds, which is super creepy. So there's a lot of really bad things you can do with this, and they're increasingly being used for espionage. And this is a hard domain to secure because it's difficult to know who to work with, and these get abandoned very quickly. Now, who cares about hacking transportation, like the trains and things like this? Well, random hackers are actually very effective at this. There's an example of a 14-year-old boy in Poland who took control of the train system in his city and was causing derailments and injuries and things like that. And if a 14-year-old boy can do it, then a lot of people can do these kinds of things. So you should be fairly concerned about this. And nation-state actors would like to carry out these types of attacks because of the potential loss of life and the potential press this would get. But it's not something that you necessarily want to go and carry out as soon as you're aware of a vulnerability. You might want to stockpile them and wait for a moment when your country is particularly vulnerable to launch this, because this is certainly going to react in a very extreme response. And these are extremely long-lived devices. I know in New York City we have trains out there that are 80 years old, maybe something like that, still running in some cases. And so the updates and security support can be limited. And as you walk around, you often may see places you can plug in or jack in that could be sensitive as well. So now that we've talked some about why I think everyone in this room who works on these types of devices, or if I didn't exactly meet your area, you can probably project into it, should be concerned. Now let's think about just a device that you all probably have with you. You know, most of you have a laptop with you. Suppose you have one. Which one of these options should give you the best security overall? Using antivirus, a firewall, using some TPM, trusted boot, verified software thing, or installing the latest OS updates? So just take a second to think about it, okay? All right. So survey of experts says the answer is absolutely updating your software. Number one, no doubt, most important thing you can do on a computer system. And the reason is that old software is vulnerable software. When you look at things like when changes are done to the Linux kernel or when changes are done to any moderately complex piece of software, even many changes that look benign are actually extremely security critical changes. Okay, so it is important to apply your updates. Old software is vulnerable software. So TPM, secure boot, etc. don't tell you that software is current. They just tell you that at some point in time, this was an okay thing to run. So it is really important to have updates. Updates are key. And I will say, to quickly go through some of the other answers, firewalls are good. You should use firewalls. They're important to segment networks and separate things out, but they're certainly not the most important thing to use in most environments and most scenarios. And antivirus, if you're running Windows on your laptop, then you should, Microsoft provides you with very nice antivirus software. If you're paying for antivirus, you're probably being ripped off. So, okay. Okay, now let's look at this set of companies. So we have here a bunch of major tech companies. What do they all have in common? They have top-notch security teams, good security records, but they've all actually had their users attacked via issues with their software updater, okay? And if these companies can get this wrong and have problems, then this is something that I'm sure should scare everyone in this room. All right, and we'll talk a little bit about why that is in the case. So first of all, I think it's obvious that updates are inevitable. You're going to have to update software at some point. And let's think about cars for just a minute to make this more concrete. Lots of code. You'll have regulations that might change, that might require things to change, and so on and so forth. And in the past, in the automotive case, recalls are extremely expensive. If you have to actually take devices in or pull in hardware, pull things back, that's just so cost prohibitive. So in practice, you need some way to update things in the field, as I think everybody should realize now. And updates are actually, like, the ability to do an update to a device is like the key thing to do to take control of a device. Because when you think about it, you think about all the attacks that you might have learned about, when you took a security class or just reading about online. You hear about, buffer overflows and use after free and ROP and all these like advanced, attacks that people are coming out with. What are those all about? It's about the attacker wanting to make your computer do something that they tell it to rather than what it was programmed to do. But if I can just push a software update to you that you think is valid, that has my code in it, then I've won. I have everything, right? So like this is the holy grail for hackers, is to be able to do software updates on a device, okay? And nation state actors use this holy grail repeatedly. So, when allegedly the United States and allegedly Israel wanted to go after centrifuges in Iran to shut down their nuclear program, they built two pieces of malware, Stuxnet and Flame. And the much more advanced piece of malware was the Flame malware, which was on the more traditional PCs rather than the embedded systems. And this spread through Windows Update in order to go and do this, spread through two flaws in Windows Update. And when North Korea allegedly wanted to attack South Korea, back when there was the whole, anyway, it doesn't matter. But they've had a lot of disagreements over time. But back in one of their disagreements, they used a mechanism in software updates and like configuration management to cause about $750 million in damage to their system. And also, of course, we have the NotPetya example, which was allegedly Russia going after Ukraine to talk about software updates. So one thing to worry about with a lot of this is nation state actors pull off extremely complex attacks. Okay. We'll talk a little bit. I'll talk a little bit about the SolarWinds hack that happened, but it was not something that just a 14-year-old boy who happens to plug into a network and is interested in whatever is going to be interested in trains is going to be able to pull off. It was a smart, well-resourced attack, and so you need to design systems that assume that attackers are going to be successful in some parts of what they're attacking. So what kind of things do you have to worry about in order to do this? So I'm not actually going to go through these, so you don't need to read this, but this is just meant to show you there are long lists of types of attacks that you need to be concerned about to build and design a system to do this securely. It is not something where you sit down and think for an afternoon and come up with a solution, okay? So you need to be concerned about many things. So let's see how people try to prevent these attacks. And first, we're going to look at some examples of what does not work, okay? And these are basically the designs of the companies whose logos were on the slides before. In most cases, in many cases, the designs they were using 5-6 years ago, and many of them have moved to TUF or other designs we're going to be talking about later on. Okay, so traditional solution one is, hey, I'm just going to use TLS. So there's just going to be some key on the repository, and then what's going to happen is there's some way that I tie this key to the repository either through the traditional CA system, or I bake the public key into the devices that I put out so that they know where to get the update from. Okay, so what do we really need? Okay, we want a design that lets us survive a compromise of the server, compromise of keys, compromise of things that could reasonably be compromised with the minimum possible damage. So we want to be able to minimize the damage of a single key being exposed, be able to revoke keys. This is really important because if you don't have a way to go from a compromise back to a secure state, you're in a lot of trouble, right? And you have to prevent a bunch of other things here. So I first got started in this space, as I said, a long time ago. I was just starting my dissertation work, and I designed the first package manager used for what we now call the cloud. And in this process, I found serious security problems in the design, not the implementation, but the security design of the way that the 10 most popular package managers all did their signing and verification of packages. So, and I showed that I could compromise millions of devices, and I worked with the distributions to upstream this. And then I wrote a paper about it because, being a naive young academic at that point, I thought writing a paper and even upstreaming things, even like working with people, that means I've done my job. This problem will be solved for all time. I'll never have to work on software updates again. Then some folks from the Tor project came and said, hey, we read your paper. We really liked it. Can we come visit you in your lab and spend some time and you look at our updater and help us design a better one? And they said, how hard can this be? So they came by for, a couple of folks from the Tor project came by for 3 days or so. And so then they went and came up with, they said, we know we don't use TLS, so we can add signatures this way, but then you have a problem with replay attacks, and if you do this, and you have a problem with freeze attacks, and so on. So we worked through this over a period of 3 days, worked through a lot of the parameters with them, and then they went away. And they said, hey, we have this thing called Tandon, this awesome software updater for Tor. It uses a few different things here based on what we discussed. And we want you to review this and just take a quick look at it before we go live with it. And so we did, and we found 8 serious security problems in this, including 3 that would let any man in the middle root all users of Tor. Okay? And at that point, it really sunk into me that it wasn't the kind of thing where we could tell people how to build a secure updater and it would happen. We had to sort of provide it for them and provide them a library and mechanism to do that. And at that point, we started the TUF project, where TUF is meant to be something that you can drop in and use as an updater that provides you with this compromise resilience. It secures software updates. It assumes from a very serious threat model. It assumes that your servers will be compromised, your network could be completely compromised, keys can be stolen or used by attackers, and Tufts tries to minimize the impact of this so that if and when these things happen, you don't end up having your users have rooted copies of things all installed. And importantly, this isn't some crazy blue sky academic thing where you have to change the entire world in order to make it happen. It layers well into existing systems. So Tufts design is based on 4 different key principles here. The first is, and I'm just going to talk through these at kind of a high level just so you have some idea about how this works. So the first is responsibility separation. So the idea here is that rather than have one key that's responsible for all the types of things you might want to do, such as being able to say, this is an authentic package, or this is the latest package, or this is the correct key to trust for to use for this specific role, we split those apart. And so the example I just gave here is a key that's saying this is a correct version of this package is different than the key that's used to say there has not been an update in the last 10 minutes or something like it. Because this key, as we'll see, if you're trying to say repeatedly there hasn't been an update recently, there hasn't been an update, oh, now there's an update, you need to use that key all the time. But when it comes to actually signing and pushing a new release, you maybe only do that, depending on your model, you maybe do that daily, or you maybe do that infrequently, like on average once a week or something like that. So those keys can be managed differently. Another idea here is that you minimize the key and role risk so that because the expected damage you're going to have is roughly about equal to the probability of that happening with the impact. So if you have a role that's a really important role, then you need to have it be very unlikely that this is going to be compromised. So in our system for root of trust, what typically happens in most of our deployments is that different people at that organization have keys in YubiKeys or something like it that they keep in safety deposit boxes in different areas. And some group of them may have to come together in order to do something like deal with a really catastrophic compromise. But that also means that if an attacker wants to compromise this role, they have to pull off a Mission Impossible style heist where they simultaneously get into lockboxes at a bunch of different places and are able to get key material. Whereas if you have a role that needs to be used, online all the time, you want the impact of that role being compromised being very low. So if this timeliness key, if the key that deals with that is compromised, then you can lie for a short period of time and say, hey, there hasn't actually been an update, in the last few days when maybe there has been one. But the actual impact of this is very minimal for your users. They might be, a day or so behind. Okay, another thing that Tufts supports is multi-signature trust, where this is like the 2 men in the submarine who have to turn the keys at the same time to launch the nuclear weapons. You can do this and say, in order to release something, both a person from our development team and a person from our QA team have to both approve it, for instance, or do other things like that in order to make things be considered valid. Yeah, and I already kind of said that. And so if one of those keys is compromised or you have a problem, it's not a real issue. And the last is, Tufts is really unique when it comes to most popular deployed security systems. Anybody who's had to deal with revocation for X509 in the whole CA system we have now knows that that's just a disaster. It just does not work well. Anybody who's had to deal with revocation in GPG or PGP, it is horrible. It's a mess. And if you have an example of a system that does revocation well, please tell me. Right? I literally, I've had people ask me, what's an example besides Tufts that you think really does this well? And I sometimes ask the audience, and I've never had somebody really volunteer one and be be strong about it. The reason why I think we ended up doing this right is not because we're more clever or anything like that, but at the very beginning, this was a primary goal of Tough. Because if you want to recover from, be resilient to compromise, you have to recover securely. And because this was always a goal from the very beginning, it wasn't something that got done in the 1.1 release or 1.2 release bolted on. It's so fundamental. So we do explicit revocation where you can say explicitly, like, this should no longer be trusted. Tough also has this notion of implicit revocation where after a certain time, this thing should no longer be trusted. And these mechanisms are both really important for security in practical situations. Okay, Tough is widely used in industry by all kinds of prestigious companies and organizations here. It's a Linux Foundation project at the highest level, the Linux Foundation inside the Cloud Native Computing Foundation. And yes, we're very happy with all the support that the CNCF and Linux Foundation have given us. So now I'm going to talk a little bit about automobiles, which present a whole bunch of unique problems because they may have 30, 40, 50, even as many as 100 different computers in them that need to be updated and have very limited connectivity and so on. So back in 2015, maybe a little earlier than that, someone from the Department of Homeland Security reached out to me and said, hey, there's a problem. The automakers need a way to secure their secure updates to their vehicles. Would you be interested in doing this? And I was like, yes, this is great. And started work along with a couple of other researchers at groups at the University of Michigan and Southwest Research Institute on building this as kind of a industry, government, academia, collaborative project. And so we built something called Uptane, which is, you can think of it kind of as the automotive variant of Tough, but it's really more of a variant of Tough that works well on more embedded, closer to embedded devices. So it's probably 99% of what you need for almost all IoT situations. And I'll talk about what to do about that other 1% later in the talk. But it has a couple of interesting things that we didn't use in Tough because of the way that Tough works and the threat domain and other things like that we had to build on top of it, that I'll talk briefly about some of these in a moment here. So as before, Uptane's goals are to prevent attacks, have compromised resilience, and minimize damage. So basically the same sort of stuff as Tough, only applied to an automotive domain. So one natural thing that you need to think about and worry about is the OEM will need to do things like tell an ECU which images it needs to be installed. And so the way to think about it is your campaign management, your choice of what to install in a vehicle, is also if you keep the keys online that say what things are authentic and use that for campaign management, then you have a real problem because a repository hack will compromise all your users. If you keep your campaign management keys offline, you can't, right? Because you have to use them all the time for your campaign management, right? Does that make sense to everybody? So one of the innovations we sort of had here was a way to combine it so that you can have one repo that basically says this is the set of valid images that any campaign might use. And then you have another repo that says, okay, we are pushing this campaign out to this specific vehicle, right? So image repository is the valid list here, and let me go through director. Okay, and then what you do is a vehicle will go and get the list of valid things from an image repo and then be told which things of that list it should get from the director and then do the installation inside the vehicle. The primary ECU is something like your telematics unit or some other powerful unit in your car that has an outward network connection, and then it can go and push those updates to the individual ECUs that are in the car, some of which have more computing power and some of which have less. So I hope that general idea makes sense. And the basic timeline for this is that we got the initial grants and then started to work with a few other organizations to really build this kind of industry, government. We had regulators and everybody in there from organizations around the world from the very beginning. We then started holding workshops. We standardized it under IEEE ISTO, and officially joined the Linux Foundation under the JDF, released a standard under the Linux Foundation, and have gone and continued to push and promote standards. We're on standard 2.0 of this now. And one thing I want to say about this is, it might be scary to some people to hear that we started at, we had our 1.0 in 2019, and it's 2022, and we have a 2.0. Okay? Because that seems like it's moving kind of fast. Well, really the only differences that we've had from the 1.0 until now, from a code standpoint, are almost zero. If you take a 1.0 implementation, the actual changes you need to make it 2.0 are effectively zero in most cases. The things that we've done, though, is sometimes we've taken a must and made it a should, or added clarification around some of the text or other things like that. And some of the musts to shoulds force things like us to bump the major revision number, should to must to should. So it's constantly worked on, but like all of the work here is basically copy editing work to make it read more like a better formal standards document than any actual changes to the system. We also have a deployment best practices guide that we've released for it, and has been contributed to by a lot of different folks, even though the automotive industry is very, very shy about anybody doing anything publicly. We have done a bunch of outreach with it as well. There are a bunch of white papers, tutorials, other things like this in a variety of formats and languages and things like that about how to use it. Optane, more recently, we have been supporting, doing work to support better integration into earlier stages of the software supply chain. So if you have compromises, these are less problematic for you. And I'm going to be talking a bit about that. There are also a bunch of different implementations of Optane, including the excellent Actualizer implementation, which is an open source implementation used in a few different places, including automotive grade Linux and also the Toradex Horizon product. We also have workshops all around the world if you're interested in joining or knowing more. So I'm just going to wrap up this part that I've talked about so far about Tough and Optane. I think that these projects have been successful in part because we worked a lot with industry, we worked a lot with government, regulators, and other people like this. And we have an open design. Everything, by the way, everything that I've done and everything I plan to ever do in the future will be open and free for anybody to use for any purpose. Open source, open design, etc. And this is really beneficial because it makes it free to experiment with and use. It's easy for end users, easy for adopters, and so on. And also, when something does happen, when there's an incident in the news, and I'm like, hey, I went to this company, I told them there was a free solution available, it's been heavily audited, it's the best standard, and why they didn't use it, we don't know, but now their users are paying the price. It feels a little different than me saying I tried to sell them my product, but they didn't buy it. You know what I mean? So, okay. Now, so far, all I've really talked about is how you take something that is a package that you signed and you want to distribute and get it out to the users. Now, I'm going to pull back a little bit and talk about a whole software supply chain and focus on what this looks like. So this looks kind of similar maybe to something like your software supply chain. Maybe yours is a little more complicated, but I hope you'll humor me for a moment, where you have some kind of repository, maybe a Git repository, and you do some static analysis and linting and stuff like that over your code. You build what comes out of your signed Git tag here, and pull in dependencies maybe to do different things, and then you fuzz and do analysis on it, and you package it and send it off, and so on. Localization, and I'm ignoring some, a few steps in here, but this should look pretty familiar. So for the moment, for this talk, to not make this like too long, I'm going to simplify a few things. First of all, I'm just going to take all this testing stuff that happens and just say there's something testing, okay? And I'm going to assume you all know how to test your stuff better than I'm going to be able to tell you to test it, at least, right? I would hope so. Because it's very domain specific and so on, right? The other thing is that I will talk about dependencies, but I'm going to leave this out for later. So right now, we're going to just drop down and imagine that our software supply chain looks like this, okay? And this is actually a big problem. Attackers can go and break into different parts of the software supply chain. And there are many, many instances of this happening. So people breaking into version control systems, like the FSF, which has Apache and all these other very high-profile projects. The FBI or possibly the NSA broke into OpenBSD's IPsec stack. Juniper's VPN was backdoored by the NSA. The Linux kernel source code repository was hacked, and so on. So this has just happened time and time and time again. Like, it's just repeated. Okay. People have also broken into build systems repeatedly. There's issues where Apple has had with people breaking in and like distributing misbuilt area things of this. There's a Fedora example I talked about before. BSD has a problem, and then SolarWinds is the big one that everybody knows about, where Russian hackers go and they break into a build system, and they install a Trojan that waits for them to do a build, and then at that moment replaces a single file with a backdoored version so it gets built in, and then removes it from the file system immediately afterwards in a completely invisible way. So it's super, it's like super smart the way they did it, and was very hard for the team to find. So this is, scary stuff. Okay, and then there's also a bunch of issues with the packaging part, and I already talked about these before when I was talking about all the problems that of companies that were broken into through their package manager. So I'm not going to beat that one to death. And then finally, for testing, there are actually a lot of situations where big companies have had problems with testing, and a kind of fun example of this is one that happened with Windows a while back, where they pushed an update that mostly went to update servers serving places like Kazakhstan. And Kazakhstan has not the best human rights and surveillance record, right? So when Microsoft pushed an update that only seemed to go to Kazakhstan and a couple other countries, people were very suspicious that this meant that Microsoft was intentionally letting Kazakhstan backdoor their users in some terrible way. But they said, no, it was just a mistake we made. Sorry. And then 2 weeks later, they did the same thing with different countries. So maybe it was actually a mistake because they may have screwed up twice, But yeah, so this happens, and it's happened to Apple and other companies like that too. So it's not, unbelievable. So hackers can and will and have broken into all sorts of different parts of the software supply chain over time. So now, how can we fix this? Okay, so there's many good point solutions. So when you look at what should you be doing on your version control system? Well, you should, I assume everyone's probably using Git. You should sign your Gits and tags that uses our code and stuff like this. Only push to production your tagged releases. I'm going to talk about, I put a little asterisk here because I'm going to come back and talk about how you make sure this actually happened later. You can't actually do this with just what I described. And you want to use hardware tokens on your developers if you can to try to, so that you have some assurance that people who are signing your code are actually, or producing your code are actually who they say they are. Because a lot of times, there are a lot of things you can do with breaking into repos and so on. You want to actually enforce your code review policies, enforce branch access control, and there's a great blog post I put here by someone who did a group that did a very detailed integration of all of this that talks about all the pain points they had and how things went and so on, if you're interested in more information. So you can kind of solve your version control issues maybe 70 to 80% of the way of where they need to be by doing the steps described there. Okay, now let's take a look at what you can do in the build system. So there's all these things we know about, TPMs, HSMs, stuff like this. So good approaches, there's this thing called reproducible builds. Who here has heard of reproducible builds before? Okay, so many of you, but not everybody. So it's this idea that you can take a piece of software and build it potentially on 2 different systems and end up with an identical copy of the software. And if you think that just sounds like it should happen anyway, then you're probably like most people who haven't tried to make things build reproducibly. But there are actually a lot of things that go into the binary that you produce that that make it vary. And so even things like the type of file system it's on might cause the order in which, when you ask what files are in a directory, they're returned, and that can cause like a linker to link things in a different order, or other things like this. There's just a whole bunch of different things that vary here. So if you can, you would want to have independently managed build systems of different operating systems that are both fully patched but are independent. Build your software and then cryptographically verify that they're the same. And what I mean by that is, don't just have like one of them take the result from the other and then only continue if it's okay, because what if that one was compromised, or what if the other one was compromised? So you want to, once again, think about a situation where one or more of your build servers is compromised. That's why you're doing this in the first place, right? So you have to have a smarter way to verify, and I'll talk about that smarter way in a little bit. Okay, so TPMs, HSMs, and things like that are good. They're nice to have, right? It's good to have that kind of stuff, but it's not sufficient, okay? It's like, like a firewall. A firewall is a good thing to have to protect your networks, but it's not the be-all, end-all for security. Once you put up a firewall, you don't just stop caring about anything else. All right, and if you're doing provisioning in the cloud, you can use projects like Spiffy, which is another Linux Foundation project, things like that to provision things. And there's a keynote talk here that was given. I think this is actually SolarWinds talking about how they changed their software supply chain to add reproducible builds and in toto and other things like that after their hacks, so that it will never happen to them again. But it goes through quite a detailed description of a lot of these points. All right, so now we have packaging. I don't really have to talk too much about this because I've already talked about all of this. But there's a couple of entries here. Use tough Uptane, or this is a popular cloud tough implementation that's done by Docker folks. Okay, and then one thing you might have heard about, who's heard of software bill of materials? Okay, also quite a few of you. So this has become a big buzzword because what this basically does is it basically describes all of this here, right? And that's important because right now, when you get a piece of software, you basically, it's like, back in the olden days in America in like the 1800s, you would buy Dr. Cappos's magic elixir, right? And who knows what's in it? It's probably heroin, but there's something in there, right? Okay? And you had no idea, right? And that's where we are today with software, right? You have no idea what's in your software, but you're just sort of okay. Now, if I go, buy something in a supermarket today, it has a list of ingredients, right? If I buy a drug, it tells me what's the active ingredients are and how much, and there's all these safety protocols. And so software bill of materials is kind of like that. Now, wouldn't that be nice? Does that solve the problem? Well, let's see here. So no, it really doesn't, okay? And so there's a lot of reasons why it doesn't. One of them is that you don't know that the thing that you built when you build your code is actually a tagged like release out of your system. You don't know that the thing that got packaged was the thing that you built, right? There's no verification for any of these, like that this process was followed. You don't know that the thing that you're going to run was the actual thing that was tested. And if you just have a single box that is supposed to track and do things, it's not going to be able to tell you all of this. You need something that effectively tracks and validates and presents cryptographic metadata for these steps. And also, you can put anything you want in software bill of materials, right? It's just a file. So wouldn't it be nice if you actually had some reason to believe this is accurate? Okay? And this is actually something that we were shouting about the time the executive order was coming out, because there were sort of two camps. There was the camp of, let's make everybody do SBOMs, and then there was the camp of, let's make everybody do something like SBOMs. It could be SBOMs, but let's make them actually signed and mean something. And unfortunately, the camp of let's just do SBOMs was the thing that was required in the executive order, but now everyone that I know is in the, oh, we made a mistake and we should have signed things camp. Okay, so let's look at what we do if we think about we should have signed things, where that takes us. So we want to verifiably define the steps of the software supply chain, verifiably define the authors, and guarantee that everything happens. So our goal here isn't just to produce a document to say, here's what we think should have happened, but to have a way to gain some level of assurance that this is what actually did happen. Does that make sense? And have that be machine verified, not require humans. So the way this happens is in Toto, you have something called a layout. And a layout is kind of like what the SBOM is to some degree. It describes these are the different things I have in my environment. Oh, I have a VCS, I have a build system, I have packaging, I have testing of different types. It also describes that there are different functionaries, there are different parties that have keys that do these things. So for instance, Bob is the developer who's always the one responsible for tagging the release that's supposed to come out. And Carol went and generated a key that lives on our build system and that is automatically used by the build system to sign things that it does. Does that make sense to everybody? Okay. And then you have things that go in and out of these different steps. So for instance, you have your signed get tag here, and then this is the thing that's supposed to go in to the build system, and then the build system comes out and produces a binary that's supposed to go into what's packaged. And then you link all of this together with artifact rules. So basically your layout says that, hey, testing has to be done over the signed tag get release, and then that signed tag get release is the thing that has to be built, and the thing that comes out of that compiler is the thing that has to be packaged. And if all of those things are true in this layout, then this is a valid version of this software. Okay? Everybody kind of get the idea here? Good. Okay. And then you sign this by a project owner, which lets you do things like revoke and change this over time. So if you decide that you don't just have one silly step here that just does linting, but you're actually doing fuzzing as well, and you add a step for fuzzing, then you would add that into your layout. And then next time you generate your software, you would expect that there would be links for your fuzzing as well as links for the other parts that we have here. All right, and then as you actually do the steps, you do something very simple. So when you go to do your testing step here, you just would do your normal command, only you'd preface it with a little prefix that looks something like this, like in toto run. And what this will do is this will automatically generate a signed piece of information that contains what went in, what came out, and a signature from this party that says exactly what's happening in the system. In this example I have here, each of these 4 steps has a party go through, generate a piece of link metadata, and then with these link metadata and the layout and the thing it's over, you can then go and check this and cryptographically verify on the end user that everything happened the way it's supposed to happen, right? And there's a few really interesting things we found. And by the way, usually, you may think, well, this might be a bunch of files. Usually just stick it in one file and distribute to the end user. Just like if you look at what a package or, when you package things now, you typically plop a bunch of stuff together in a package. But one kind of interesting thing about this is we accidentally, by doing this, protected against attacks we weren't trying to protect against. So I can give you an example of one of these. When you go and you unpack packages on a system, there's a type of attack that Android and Fedora and a few others had problems with, that dealt with if you have duplicate copies of something with the same file name inside of an archive. They were doing a check over one copy, but then they were using the other copy. So for instance, when you unpack the first one, you would say, okay, this is the one I'm going to check like the hash of when I hash the package, but you would actually replace it with the second copy in there. And so for a while, and actually my former student found and fixed this in Google about a month after he finished working for me. He went there to work on their package security team for Android, and found that that he could have compromised and caused big problems with basically all Android packages because of this. So in Toto, you just naturally protect against this because it's natural to say, when I unpack the things, they should be the same things that came in, right? It's just like, of course. And so in Toto automatically flags us and says, hey, there's something wrong here, even though that wasn't a bug we were ever trying to prevent. We hadn't thought of that. We hadn't thought of that when we were writing our layouts and things and testing it. So within Toto, you end up writing this layout, and it's actually very simple to go and generate this link metadata. In fact, I had a quick chat with Brandon after his part of his keynote earlier today, and he's already generating a Horizon build system link metadata and stuff like that. So hopefully, like a soon future release of this will have all of this all built in. But it's actually surprisingly easy to integrate. So you go, you have your layout, you have these other things, you have this final product, and everything is checked and verified that the process you said should happen is what happened. Okay, and that's what Intoto is able to do for you. If you don't use Intoto, even if you use good solutions at different individual places, you're still going to run into quite a few problems because hackers can get into your system in lots of different places. Okay. It's been integrated lots and lots and lots of different places. It's being used by thousands of companies and is really being pushed by Microsoft and Google as potentially like a industry-wide standard for some parts of this. So we're also continuing to really aggressively try to push this forward because not because we want to sort of win, but because the other things we've seen in this space have had pretty obvious flaws, and we don't want to sit around and, even though it's good for me to write papers for the next 20 years about how bad all these other things are, I'd rather just have them not impact users' lives. Okay, so for software supply chains, use Intoto. Securing the whole software supply chain is important. This is the first tool to secure the whole software supply chain. I think we released the first version of this in 2017 publicly, or at least I think we had our first adoption release around that time. And one thing we did when we did this is we spent a lot of time working together with my team, red teaming very subtly different designs for this. And what that's meant is we know where a lot of the problems are if you don't do things in quite the right way. So what we have has been adopted in a lot of the other like popular things you might know of, like SL, Salsa, the thing underlying GitHub, and SigStore, in part because in many cases, engineers from those teams would do a design, and we'd say, wait a minute, that was a design we thought of a while ago, and we realized there was this problem with it. So we reach out to them and say, hey, you have this problem if you do it this way. And then they say, oh, yeah, that's right. Okay, we're going to do this instead. And then we'd say, oh, yeah, well, if you do that one, you're going to have this problem. And then after doing that, usually 2 or 3 times, they say, okay, well, what should we do? And then we're like, well, you should use Toto. So that's why we're kind of underlying a lot of the other technologies out there in the space. It's a Linux Foundation project. It's free, open source, open community. Encourage you to experiment with it. So to kind of wrap up the last little bit of my talk here, I'm going to do rapid fire on a few important topics that don't neatly fit into exactly software updates with tough Optane or software supply chain within Toto. So what should we do with our dependencies? Question number 1. Okay, so avoid big dependency chains. So NPM is a really, the whole Node.js NPM environment is really terrible for this. Where Discord, which many of you have probably used, has about 20,000 packages and about 40,000 developers have contributed a line of code that's in Discord. That is insane, right? Okay? So avoid ecosystems like that if you at all can, to be bluntly honest. You need to validate your dependencies the same way you sort of validate and trust your own code. So looking at things like, is it maintained? Is it well engineered? Has it been audited? Are they actually producing releases in a secure way? Because a trend has been that people will take over either developer accounts or even just kind of buy a project from a developer, sometimes by contributing for a while and then taking over or doing other things, and then use that to distribute malware or put backdoors in systems. You also do absolutely need to update your dependencies frequently and be worried and trying to do this, because once again, old code is very likely to be vulnerable code in many cases. You can look to see, am I even using this code path or things like that, which I strongly encourage you to do, but don't have old dependencies around, or you're going to end up with all kinds of log4j, whatever, issues. And you need to recurse. So if your dependencies have dependencies, you need to worry about them as well. Okay, what about offline updates? What if there's not a repo? Okay, so we handle this in Tough and Optane. And Optane has something called a Pure, which is their way of changing the standard that addresses this. Tough also has some support. Actually, a lot of the work in this has been done by the Toradex folks. So they have a really nice blog post about this. But if there is another part of that, 1% that isn't being covered here that we're not aware of, tell us. We want to know. We don't sit in our lab and dream up the weird corner cases that you all run into and fix them. You all usually tell us, and then we fix them. And sometimes, often, especially in automotive, we get told we can't say who said this, and that's fine. We can deal with that. But we need to know where the problems are at, if there are problems. Okay, so let's say I have a software supply chain, and I want to go from where I am to somewhere better. How do I do that? Okay? You generally get the most security value. First of all, fix anything that's badly broken. If you are just getting or curling code off of some repo on the internet as part of your build process for bringing in dependencies, then fix that. Don't do that. After that, probably the next easiest and next most valuable thing is probably to use Toto to document your process, because this forces you to understand your process. And actually, just the act of understanding what you're doing and how you're doing it can be very informative for people, especially if you weren't the one who started the project. I've been in a meeting under NDA, I can only say a little, with a top 5 tech company, and I asked what I thought was a very simple question. And then after I asked it, everybody looked at each other, and then someone ran out of the room. And 2 hours later, they released a security advisory. I didn't get credit for it, but they released a security advisory for something. So knowing what you're doing is really important, and it's not that uncommon, okay? After this, you probably want to turn on, if you're using GitHub, like multi-factor authentication, or you want to enforce Git signing in some way. Ideally, you can use YubiKeys or something like that. They're super cheap. They're usable. There might be some developer resistance, but they're well worth doing if you can do it. Things like Tough or Uptane, if you have to do them yourself, probably fall in here. Sometimes you'll get a product that wraps a lot of this up for you, so it might actually be easier. Then you need to start to audit things like your dependencies. And then after this, probably the hardest one to do is to do things like reproducible builds. This actually requires a fair amount of work in a lot of cases. So, but if you can get there, it's worth it. And yeah, as I said, this list is roughly in order from easiest to hardest as well. So start at the top and work your way down would be my suggestion. All right, should I make my own supply chain, security system, schema, whatever? I wouldn't do that. Just in general, it's a really bad idea. If everything you're doing, your hardware, your OS, your compiler, your repository, your client devices, everything you're doing for yourself and only using yourself and no one else ever needs to validate anything you're doing, then maybe you can do it, okay? But in practice, this just doesn't happen. So you should just use like open standards that exist for how to specify this information. And some of these are also flexible. So if you have a field that nobody else has because no one else cares about the amount of voltage going into the build farm when you do a build, which I don't know why you care about it, but whatever. If there's something that matters to you that doesn't matter to anybody else, like these frameworks have extensibility, so you can specify them that way. And you also, I want to urge you, when you make this change to document what you're doing, you might as well sign the damn thing and might as well use it to check things, because that's going to be the next frontier of us nagging people for 5 years to fix things. So cryptographically sign and verify it, and that's basically always going to be using in toto today. Okay, so what about blockchain, post-quantum crypto, whatever the latest thing that somebody higher up than you read about in a magazine and wants you to look into, okay? Well, that's what we get to do. We're academics, right? We get to like try some of this stuff out. So there is actually a post-quantum crypto support for Tough in a branch off somewhere that you could play with if you wanted to. There's IPFS, like a blockchain technology support substrate for Tough in a PR, right? There's all this sort of stuff out there. And so, if you want to look at something or explore something or show something to somebody, you can probably do it. Now, these are not parts of the specification. It's not something that if you use Uptane, you have to use, you will use blockchain or whatever. It's just not that way. But if you want to experiment with something that's a little further out there, we might already have a branch somewhere that you can play with and show. And if we do get enough adoption of something, then we can make it optional in the spec or a supported thing if it becomes an important use case for people. Okay, how do I secure hardware components? Suppliers are really key. So I think the hardware security folks are much further ahead of things in software supply chain. Like hardware supply chain folks have realized we have to worry about who's making our chips for quite a while now. And the software folks, I think the SolarWinds hack was a big wake-up call for a lot of people. So you may see tools that try to tell you what is in a piece of firmware and provide you with like a scan of that information. Okay, they're actually very good for catching bad practices, like somebody who builds something and puts a bunch of stuff in there because they don't know what they're doing. But they will not catch someone who's trying to hide things, someone who's actually malicious. Okay? And I think that the salespeople of these tools will not tell you this distinction. Okay? So I'm not saying that this value proposition here is bad. Like catching people who do stupid stuff is good, but they're just not going to ever be effective here. Okay? Just fundamentally for a bunch of reasons I can talk about some other time. So you should just track your hardware supply chain firmware using known techniques. I claim that in toto can handle this because we've had a few different groups talk with us about stuff they're doing there, but they're really small groups and we don't really have any public data we can make public. So if you do try to do this, please chat with us about rough edges, ideally producing a blog post or white paper we can talk about. If this doesn't work perfectly and you have things that need to be tweaked or changed, that would not surprise me, right? I mean, these specifications and these systems didn't come out fully formed. They came with partnerships, okay? How do I get an Optane or Tough or whatever for domain X? Okay, so this is not as relevant because you can, buy a version of it that's been nicely customized in general for IoT domain. But if you need, for some reason, something without that, where there needs to be something that's more customized, then let us know. Our projects have very heavy community collaboration, lots of participation from different groups. Share problems with us, ideally on the record. You help us convince government and regulators, and then we get our money from government and regulators. We actually don't take money from industry. So this is intentional because usually if I were to go to, like I'm going to Cloud Native Con next week to speak there, and if I were to go give a talk and say this is, a product that is paid for by Microsoft and Google, then, a lot of their competitors wouldn't be very happy to perhaps use it. So the fact that we're getting our money from the government and not from industry is actually beneficial in some ways for adoption. And even if it's not funded, we will help you. We have not had funding for Tough for most of the lifetime of Tough, because Tough has been around more than, it's been around more than 10 years now. And Optane, we haven't had funding for the last 3 years or something, but the project is still growing strong and accelerating in use and stuff like that. We just have to lean a little bit more on our industry partners to do things that otherwise we would do internally. Okay, so last slide, wrapping up. Securing devices is a major challenge. Nation-state actors are definitely more aggressive than ever before, so this is something you should really be worried about. Regulation is increasing in this space, but fortunately tools are also improving, so there's lots of stuff you can use here. If you have things you need, you have problems, or you try to use some of the stuff we're doing and you have issues, or you want to know if what we're doing actually applies well, then reach out. Talk to us about problems and pain points, and with the right effort, you can be in the group that stays ahead of the attackers. So thank you very much.